Hello everyone, welcome to the 8th lecture of CE 202 Structural Analysis 1, that is Moving Loads and Influence Lines. So this is the continuation of lecture 7, and in the lecture 7 we discussed some problems related to the a series of concentrated loads moves across a span. So this is the continuation of lecture 7. Okay, so problem number 3, in which a load system as shown in figure crosses a girder of 25 meter from right to left with a 60 kilonewton load leading. Find the absolute maximum bending moment and state where it occurs. Also find the maximum bending moment at 15 meter from left end. So here the difference in this question is in this the series of loads that is moves from right to left. So consider the simply supported beam AB on which the section C is marked here. It is 15 meter from left support A, and consider the series of loads in which the 60 kilonewton load is leading and which is moving from right to left of the beam. Okay, so first question is to find the maximum bending moment at 15 meter from left end. So we have to find out the maximum bending moment in the section C. So here Z is equal to 15 meter. So how will you locate the maximum bending moment? So we have to consider each load, and each load is crossing the section C, and we have to find out the average of each load. So consider the first 60 kilonewton crosses the span. So the load crossing C is 60 kilonewton. So the average load on AC is 60 divided by 15, that's equal to 4. And the average load on CB it is 24. So the difference is minus 4. Now consider this 80 kilonewton is crossing this section C, and the average load on AC is 9.33 kilonewton, and the average load on CB it is 16 kilonewton. Now the difference is minus 6.67. Again it is negative. Now consider the next load, that is 60 kilonewton is crossing the section C, and take the average load on AC, and it is we got it as 13.33, and the average load on CB it is 10. So the difference is 13.33 minus 10, that is 3.33. That means when the 60 kilonewton crosses the section C, this negative 6.67 is changed to positive 3.33. That means the maximum bending moment occurs under this 60 kilonewton. For that, place this 60 kilonewton under the section C. Okay, so I am placing this 60 kilonewton in the section C. I am drawing the influence line diagram for bending moment at the section C, so that the maximum ordinate will be under this section C, and it is Z into L minus Z by L. Here Z is 15 meters, so we got the value of 5C as 6. Okay. Now consider the properties of similar triangles, obtain y1, y2 and y3. Now the maximum bending moment, that is MC, is equal to 60 into y1 plus 80 into y2 plus 60 into y max plus 100 into y3, and we got it as 1384 kilonewton meters. Okay, now the absolute maximum bending moment. Okay, here you can see the load systems. The loads are 60 kilonewton, 80 kilonewton, 60 kilonewton and 100 kilonewton. Now we have to locate the center of gravity of this load system. For that, take the moments of each load, that divided by the total load will give the center of gravity, and that is obtained as 5.2 meters. Okay, so the center of gravity is occurs somewhere here, and the distance between this 80 kilonewton and center of gravity is obtained as 5.2 minus 3. That is, this 5.2 minus 3 is the distance between this 80 kilonewton and center of gravity, and also the distance between center of gravity and this 60 kilonewton is just 1.8 meters. So here you can see that the distance between 80 kilonewton and center of gravity is 2.2 meters, whereas the distance between center of gravity and 60 kilonewton is 1.2 meters. So the absolute maximum bending moment occurs under the heavier load falling close to the center of gravity of the load system. So here the load 60 kilonewton is close to the center of gravity since the distance is just 1.8 meters. But the next load, that is 80 kilonewton, which is more than 60 kilonewton. Okay, so that we have to consider two trials. The first one is we have to place the center of the center of the beam, that is C, in between center of gravity and 60 kilonewton, and then in the second trial we have to place the center of the beam in the midway between 80 kilonewton and center of gravity. Okay, so in the first trial the load should be placed in such a way that the center of the beam should be the midway between center of gravity and 60 kilonewton. Okay, consider this as the maximum value, that is the maximum of maximum bending moment, that is the absolute maximum bending moment. Okay, now problem number 4. The question is that draw the influence line diagram for bending moment at a point 10-meter distant from left-hand abutment on a bridge girder of span 25 meter. Find the maximum bending moment at the point due to a series of wheel loads, that is 100 kilonewton, 200 kilonewton, 200 kilonewton, 200 kilonewton at center to center distance of 4 meter, 2.5 meter and 2.5 meters. The load can cross in either direction. The load can cross in either direction with 100 kilonewton load leading in both cases. Okay. That means we have to consider first that the load is moving from left to right, and also the loads are moving from right to left, and we have to always place this 100 kilonewton load as the leading load. Okay, and the distance remains the same. So we have to consider, we have to find the value of maximum bending moment at a point 10 meter from left end. Okay, so this is a section C at a distance 10 meter from the left hand support. Okay, which is shown in this figure. Okay, and the total length of the beam is 25 meters. Now case 1, that is when the train of loads moves from left to right. That means the 100 kilonewton load is leading and the train of these loads are moving from left to right. Now consider this first 100 kilonewton is moves or crosses the section C. So that the average load on AC is equal to 80 kilonewton and the average load on CB is equal to 6.67. So the difference is 73.33. Now consider the next load, that is 200 kilonewton, which is crosses the section C. Now the average load on AC is 60 and the average load on CB is 20. So the difference is 60 minus 20 is 40. Okay, it is also a positive value. Now consider this 200 is crosses the section C, so that the average load on AC is 40 and the average load on CB is 33.33. Now the difference is 40 minus 33.33, we got it as 6.67. Again it is a positive value. Now consider this 200 kilonewton, that is the third 200 kilonewton, and the average load on AC is equal to 20 and the average load on CB is equal to 40. So the difference is minus 20. So here we can see that while the 200 kilonewton crosses the section C, the positive 6.67 is changed to minus 20 kilonewton. That means under this 200 kilonewton maximum bending moment occurs. So we have to place this 200 kilonewton in the section C to get the maximum bending moment. So I am placing this 200 kilonewton in the section C, and we got here YC is equal to Z into L minus Z by L. Here Z is 10 meters. Okay, so the maximum bending moment is equal to 200 into Y4 plus 200 into YC plus 200 into Y1 plus 200 into Y2 plus 100 into Y3. Okay. By using the properties of similar triangles, we can easily find y1, y2, y3 and y4. And the answer is 4140 kilonewton meters. Now consider the train of loads moves from right to left with 100 kilonewton load leading. Okay, so we have to redraw the concentrated load figure, series of loads figure with 100 kilonewton load is leading, and the distance between 100 and 200 is 4 meter. The distance remains the same. Now consider this 100 kilonewton is crossing section C. Now the average load on AC is nothing but 100 only. That divided by the length of AC is 10 meters, so that's equal to 10. The average load on CB is 53.33, so the difference is minus 43.33. Now consider this 200 kilonewton is crossing the section C. Now the average load on AC is 30 and the average load on CB is 40. So the difference is again minus 10. Okay. Now consider the second 200 kilonewton load is crossing the section C. And here you can see the average load on AC is 50 and the average load on CB it is 26.67. Now the difference is 23.33. That means the second when the second 200 kilonewton crosses the section C, this negative sign changed to positive sign. Okay, so under this 200 kilonewton maximum moment will occur, so that place this 200 kilonewton in the section C to get the maximum bending moment. So I am placing this second 200 kilonewton in the section C and drawing the bending influence line diagram for bending moment. Here YC is Z into L minus Z by L, which we found earlier, and the load ordinate corresponding to 100 is Y1 and corresponding to 200 is Y2 and corresponding to next 200 is YC and this 200 is Y3 and the last 200 is Y4. So the maximum bending moment is equal to 100 Y1 plus 200 Y2 plus 200 YC plus 200 Y3 plus 200 into Y4. And we got it as 4110 kilonewton meters, which is less than the previous value. So the maximum bending moment occurs when the loads moves from left to right and its value is 4140 kilonewton meters. Okay. Now we are moving on to the problem number 5. That is, determine the maximum shear force and maximum bending moment at quarter span from left end when a UDL longer than the span of intensity 20 kilonewton per meter accompanied by a 100 kilonewton concentrated load crosses a span of 12 meter. Use influence lines and the concentrated loads can occupy any position. Okay. So coming to the solution, here the length of the beam is 12 meters. Okay, now we have to find the maximum shear force and maximum bending moment at quarter span. So the total span is 12 meters, so the quarter span is 12 by 4, that is 3 meters. So Z is equal to 3 meters here. Okay, now we have to find the maximum negative and positive shear force. So when the UDL is longer than the span, the maximum negative shear force occurs when the head of the UDL is at section C, and it's about when in the case of a concentrated load, the load should be placed at just left to the section C. Okay, so I am placing the head of the UDL in the section in the section C, and also the 100 kilonewton is at the section C, and we are finding the value of this shaded area and that into intensity of load plus this 100 kilonewton load into this ordinate will give the value of maximum negative shear force. Okay, here we have two cases, that is when UDL longer than the span moves through the section and also a concentrated load. Okay, the maximum negative shear force occurs when the head of the UDL is at the section C, and also the maximum negative shear force occurs when the concentrated load is just left to the section C. So likewise place the UDL and concentrated load and find out the value of maximum negative shear force. And here you can see the shaded area is a triangle, and find out the area of this triangle by using the equation half BH and that into intensity of load, that is 20. So 20 into half into 3 into 0.25, and this ordinate is maximum negative shear force ordinate is, that is Z by L, and we got it as 0.25. So the maximum negative shear force is equal to 32.5 kilonewton. Okay, now the maximum positive shear force. So the maximum positive shear force occurs when the tail of the UDL is at the section C. The tail of the UDL is at the section C, and also the concentrated load is just right to the section C. I am placing this 100 kilonewton in the section C, and also the tail of the UDL in the section C. Okay, and find out the value of maximum positive shear force. Here you can see also a right angle triangle. So intensity of load, that is 20 into half BH, that is half into 9 into 0.75 plus 100 into 0.75, that is this ordinate, that is L minus Z by L. Okay, so the maximum positive shear force value is equal to 142.5 kilonewton. Now, for maximum bending moment, the UDL distributed throughout the span, the point load should be placed in such a way that it should be placed in the section itself. Okay, so to get the value of maximum bending moment, the UDL should be distributed throughout the span. So the UDL will occur in the entire span, and this point load will come upon this section C. Okay, so the maximum ordinate in the bending moment is for bending moment in the influence lines are Z into L minus Z by L. So we got the value as 2.25. So the maximum bending moment is nothing but 100 into 2.25 plus intensity of load into area of shaded region. So here also you can see a triangle, that is half into B into H will be the area of this triangle, that into 20 plus 100 into 2.25 will be the answer for maximum bending moment, and that's equal to 495 kilonewton meters. Okay, now so that's about the problems on simply supported beam. Now I'm just going through the influence line diagrams for singly overhanging beam and also the doubly overhanging beam, which we discussed in the previous lectures. Okay, so this is the influence line diagram for RA, and this is the influence line diagram for RB, and this is the influence line diagram for shear force at D, and this is for shear force at E, and this is for bending moment at D, and this is the influence line diagram for bending moment at E. And we already know how to draw all these influence line diagrams. Okay, now this is a question on a doubly overhanging beam. So consider this unit load is at a distant sites, and we are drawing the influence line by considering the unit load is moving from C to D. So this is a doubly overhanging beam, and this distance is A. That means the left overhanged section is A and the right overhanged section is B. Okay, now the Z is the distance of the section E from the support A. Okay, and this is the length of the simply supported B. Okay, now this is the influence line diagram for reaction RA, and this is the influence line diagram for reaction RB, and this is the influence line diagram for shear force at E, and this one is for bending moment at E. Okay, now there is a question that draw the influence lines for shear force and bending moment at a point C of the beam shown in figure. That means we have to draw the influence line diagram for this W overhanging beam. So here you can see that A is 1 meters and B is 2 meters and Z is 3 meters. Okay, and the total length of this simply supported beam is 7 meters. Now this is the influence line diagram for shear force, and this ordinate is A by L, so that here the length is 1, that is A, so 1 divided by L. Here this is the length of the simply supported beam, so L is 7 meters, so 1 by 7 is the this ordinate, and this ordinate is nothing but L minus Z by L, and that is equal to 4 by 7, and this is Z by L, that is 3 by 7. Okay, that means this distance is Z. Okay, now this ordinate is B by L. So 2 divided by 7 is this negative ordinate. So this is the influence line diagram for shear force. Okay. Now this is the influence line diagram for bending moment at section C. Okay. So this is a maximum ordinate, that is Z into L minus Z by L. So that's equal to 12 by 7. And also this ordinate is A by L into L minus Z. So A is here 1 and L is 7 and Z is 3. Just apply those values into this equation and we got it as 4 by 7, and it is a negative section. And also this ordinate is Z by L into B. Here Z is also 3 and L is 7 and the B is 2. So so that's equal to 6/7. So just knowing the influence line diagram for shear force and bending moment at C for a W overhanging beam, we can draw the influence lines and influence line diagram for shear force and bending moment at section C for any problems. Okay, hope you all understood this section, and thank you for watching. Thank you.